Hello everyone, and welcome to this video titled Linear Approximations and Differentials. In this video, I'm going to be taking you through a preview version of a Knewton Alta Homework Assignment, also titled Linear Approximations and Differentials. So please understand that this is a preview version I'll be going through. So the questions that I work on in this video may not be exactly the same questions that you'll see when you work on the assignment as a student. But the objectives should be the same, and the methods I use should be similar to what you should be using when trying to solve these problems. All right, so here we are at Knewton Alta, and this is a preview of linear approximations and differentials. And for this particular course I'm teaching, this is section 4.2. In the upper right-hand corner, you should see a mastery bar. This tells you how far along in the assignment you have gotten. Next to that, an activity log, which you can see all the objectives for the assignment here and how far along you are in each objective. So this particular assignment has 5 objectives broken into 2 headings. And I had the settings so that you could switch to a different heading if you wish to start a new heading, but I won't be doing that in this video. So the first several questions will be on the 2 objectives under the linear approximations of a function at a point heading. So then you have your current objective on the main page. Underneath that, a question related to that current objective. And then at the bottom of every question, now you have to click on the little dots here. Some problems have show steps. I haven't really done this too much in other videos, but most questions should have a feedback spot. If you notice any issues with a question or with the answer explanations to a question, you can click on feedback and send feedback directly to Knewton's support, and hopefully someone will get back to you relatively quickly to address any issue you may have. Of course, you will not have the instructor cheat feature. It's for instructors only to fill in answers for demonstration purposes. I will not be using this in this video either. You will have a more instruction button though. So if you're ever working on a problem in a particular objective and you don't really recall the material for that objective too well, or you don't remember what to do for a particular question, click on more instruction, and some instruction, whether it be reading to do or videos to watch or both, will show up, and you can look through all that material and hopefully it'll help you get through the assignment. All right, so before I get into this question, I want to do a little discussion about the first heading, linear approximations of a function at a point. All right. So just call this linear approximations. So suppose we're given a function say y equals some function f of x. And I'm going to say that this is let's say this is a continuous, differentiable function at a particular input called a. So I'll just draw a generic function here. So we got this little swoopy function, something like this. So here's the graph of y equals, f of x. And then say I would like to approximate, we're gonna go to a particular value called a. So here's point a comma, f of a. And so the output over here would be the value of this function f at input a. Then what we're going to be doing in this first couple objectives is going, off of a, plug in a value that's away from a. So let me go over here. So again, here's some value that's away from a, and this distance we are off of a here, that is some change in the x coordinate, or delta x. You might recall this from other algebra stuff. When you see this triangle shape, this delta, remember this means a change in. So this would be a change in x. So then my input over here, now the change in x could be positive, it could be negative, I could be to the left of a, but whatever. So we're at some other input, called a plus delta x. Right? I'm starting at a, and then I add this change in x. So I plug this into the function. Takes me up to this point here. So again, that point has, a plus delta x as an input, and then its output, would be called, the value of this function f, right? We're actually on the curve f here at a plus delta x. And how much the output changes, right? So I went from f of a to, f at a plus delta x. That's going to be delta y, right? So again, delta y, put this down here. So this is how much the output actually changed on the curve. So this is an actual change in y. And the way we would normally calculate this is I would take, the value of y at the end. So the value of f at this, a plus delta x input, and then we'll subtract the value of the y coordinate at the beginning. So then minus the value of f at a. And so what we can see here is that the value of f at this, a plus delta x input is equivalent, just adding f of a over here, is equivalent to the value of f at a, the original output, right, the y coordinate at a, plus some change in y, right? Just add delta y here, right? And you can see that in my picture. See, if I go from 0 to f of a and then add this change in y, I get f at a plus delta x. So what we're going to be doing in this section is this value of the function at an input off of a, or near a. So we're going to have delta x be pretty tiny here. The change in x be pretty small, so we'll be close to a, but not at a. We're going to approximate this value of f at a plus delta x, using the tangent line at x equals a. The tangent line at x equals our initial point, a. So let me draw that in. So remember what the tangent line looks like at a point. So here's the point a, f of a. So here's this tangent line, right? It's pointing in the direction that the curve is going in at that moment. So again, here's the tangent line at x equals a. Well, it's still a function. You could say the tangent line function, right? Y equals, and what you're going to see in this instruction or in this text here is, because it's a line, a linear function here, they're going to represent this, the original curve, is called f. Because this is a line, quite often you're going to see it represented by the letter L. So this tangent line function is represented by y equals L of x. And we'll get to what that, the rule for that would be in a second. So can you see now, when I plug in this a plus delta x, plug it into the tangent line function, gets me this point here. So again, input a plus delta x, and then that output, then it'll be L of, right, the value of the tangent line function at a plus delta x. And hopefully you see that, when delta x is small, this L at a plus delta x will be very close to f at a plus delta x. So that's the key here to our approximation. So when the change in x is, and I'll put this in quotes because we're not really defining it so much here, but when this change in x is tiny, you see we'll be around point a f of a. When you make a small little change in x, very tiny change in x, you see how the tangent line and the curve itself are very close to being one another. Their outputs are almost exactly the same. So when this change in x, this delta x, is small, the value of L, the value of the tangent line at a plus delta x, will be approximately, right, little approximately wavy equals sign. The value of the tangent line at a plus delta x will be approximately, the value of the function itself at a plus delta x, right? The value of the tangent should be very close to the value of the actual function, right? And we'll get into, estimating changes in y and stuff like that too, but this is key. So we just need to find the equation of a tangent line at x equals a, which should be no problem, right? If you remember your derivative. So remember that would be I'm passing through the point AF of A. And remember the slope of the tangent line would be F prime at A. So you got y minus F of A for the change in y coordinates on this line would be equal to the slope which is f prime at a, times, and then the change in x, which will be x minus a. And then I add f of a to both sides, and we get y equals the value of f at a plus, and then this, the value of f prime at a, the slope of the tangent line, times x minus a. And this expression here, this f at a plus f prime at a times x minus a, that is L of x. That's an expression for this, this tangent line function. And we're going to use that to, again, approximate the value of another function near a value called a. So it's all about tangent lines. And again, you know how to find, by now, equations of tangent lines. So look, first question here, right? We're asked to use a linear approximation, right? Tangent line, to estimate a function value. So like it says, use an appropriate linear approximation to estimate 1.998 raised to the 5th power. And we're asked to round our answer to 3 decimal places, right? The nearest thousandth. So we got to think of what functions we're going to be working with here, right? So they're asking us to estimate, 1.998 raised to the 5th power. So you got to think here, this is very close to 2 to the 5th. So this is the value. So I'm going to let a function be, some number to the 5th power. I'm going to have f of x, my original function, be, some number x to the 5th power. And then this value here, okay, 1.998 to the 5th. This would be f of 1.99. Now, if I call that f, right, this would be f of 1.998. And 1.998 is, close to, and then think of a nice, a nice number that this input would be close to. 1.998 is close to, x equals 2. All right. So let me show you what's going on here, kind of tie it to the picture I drew on the previous page. So again, y equals x to the 5th. All right, that looks like this. Odd power function here. Right? It looks something like that, right? Here's y equals, x to the 5th. That's this function I called f. Now we know that at x equals 2, right, a nice number that's better than, a nice whole number that's near 1.998, you have this point on the curve, which would be, 232, right? 2 to the 5th power is 32. So rather than plug in, so again, I go off of 2, go to 1.998. So that means that, the delta x, right, the change in x was negative. If I go from 2 to 1.998, my change in x was a negative 0.002, right? I decreased my nice value by 2 thousandths. And decrease, so negative. Anyway, so I plug this in, right? That would give me, what the value they're asking us to approximate, 1.998 to the 5th power. Well, rather Okay, rather than plug it into this function here, this x to the fifth, I use the tangent line at x equals 2 instead, right? So here's the tangent, which we'll have to find the equation for. So again, they're calling this y equals, some function of x called L of x. Well, again, we're going to figure out that expression. And then what I'm going to plug in, 1.998 to this L function, this tangent line function, giving me the value of L at 1.998. And so the value of L at 1.998, right, should be approximately the same as the value of f at 1.998 for this 1.998 to the fifth power. Right, so rather than calculate it directly, multiply 1.998 by itself 5 times here, I just need to find the equation for the tangent line here at x equals 2, again, which is near 1.998. And then we'll plug in 1.998 to the tangent line and get an approximation. So again, I brought this up on the last one. So remember this L of x, this tangent line function. Well, here, a is 2. The nice value we're at here is 2. So it's f at 2 plus f prime at 2 times the quantity x minus 2, right? This is the f at a plus f prime at a times the quantity x minus a, but now the a value is 2. All right, so we need f at 2, which we have, right? This function, this x to the fifth power function at 2 is 32, 2 to the fifth. F prime, the slope of my tangent line. Now f prime of x, right, being that this is just a simple power function, do the power rule, the derivative would be 5x to the fourth. So then the slope of this tangent line at 2 here, f prime at 2, would be 5 times 2 to the fourth power. Now 2 to the fourth power is 16. 5 times 16 is 80. So this line has a slope of 80, very steep. So here's the tangent line function, L of x. So L of x would be 32 plus, and then 80 times the quantity, x minus 2. Now, if you want to put this in slope-intercept form, you can, but I'll leave it this way. Now I just need to plug in this 1.998 to my tangent line function, and the value of the tangent line function at 1.998, I should be very close to the value of this fifth power function that I set up at 1.998. So I plug in 1.998 to this L function, this tangent function. So again, we got 32 plus, and then 80 times, and then 1.998 replacing x minus 2. And again, this pretty much is just a change in x here, which I said would be negative, right? We said delta x was negative 0.002. That's this expression in the quantity here. So we have 32 plus, and then 80 times, and then I'm going to write this, as a fraction. This is negative 2 over 1,000, right? Negative 2 thousandths is negative 0.002. Do a little simplification here. This is 8 times 10, so this is 100 times 10, so one of the zeros goes away. And then 8 times negative 2 is, negative 16, so this is 32 plus, and then negative 16 over 100, which if you want to go back to decimals, right, would be 32 plus, and then, negative 16 hundredths, negative 0.16, which when I subtract these will be 31.84. And this should be according to our picture here and what I was saying about these tangent lines, near x equals 2 here, 1.998 is near 2. So the value of the tangent line at 1.998, right, is 31.84. This should be approximately the same as the value of the function that we started with, this x to the fifth at 1.998. So here's what I'm going to enter, right, this 31.84. Now you can go to a calculator and see how good it is, right? I do have the Desmos up here, and I'll show you all the stuff I put in there by hand, right? The original function I called f of x was, x to the fifth, and you had this point, 232 on there, and I'll label it and try to move. I'll move it up so we can actually see the point, right? There's 232. And you can see right away that it's pretty steep right here, right? And we already saw that, the tangent line has a slope of 80. So here was the tangent line, right? That thing called L of x. And I said it was 32, right? The value of the function at 2, plus then the slope, right? 80 times, and then the quantity x minus 2. And you can see, right? When I turn this graph off and on, it's pretty much just right on top of the function. It's so close. All right, so this tangent line and this function that we started with are very, very close to one another around this point 232. Now, obviously, the further away you get, it's not always great, right? Like down here near 0, this tangent line at 2 is not near the graph at 0. But at the point 232, the tangent line and the function itself are incredibly close. So look, here's the actual value at 1.998. Okay, this is f at 1.998. So you see how the actual value, 1.998 to the fifth power is 31.8403196,802, right? It's all those decimal places. But that would have been, if we were asked to do that by hand, that would have taken quite a bit, right? I'd do 1.998 times itself, 5 times. But go into the linear function. So go into capital L there, plug in 1.998, and you see this is what I got on paper. The value of the tangent line at 1.998 is 31.84. So you see that's a very good approximation. That's good to 2 decimal places. Actually 3 decimal places, because you can throw a 0 on the end here. 31.840, which I will, well, I'll just type in 31.84. It's implied 0 would be the third decimal place if you do that. Yeah, so again, hopefully you're seeing that, this tangent line function very close to giving me the actual value of 1.998 to the fifth. But yeah, so that's what we're entering here. Again, you're not entering the actual value of 1.998 to the fifth. What you're doing in this is entering the linear approximation, right? The value of the tangent line when I enter 1.998, which we said was 31.84, right? So that's what I'm entering there. And I'll submit. Wonderful. And then after you submit, you should be given some sort of green or red banner, whether or not you got something correct or incorrect. And then beneath that, an answer explanation. I'd highly recommend reading through the answer explanations, whether you're right or wrong. If you are correct, but you did the problem in a very roundabout way and you start reading through their answer explanations, and you notice that they do something better than than you did, and you like it, you like the way they do things. Maybe you'll want to try that method for a question like that in the future. I would now definitely read through the answer explanation if you got it incorrect. All right, so read it carefully. Hopefully you can figure out where you went wrong, where you made a mistake, and then learn from those mistakes for future questions that are similar. Okay, so here's describe the linear approximation to a function at a point. So you see this, remember this L of x? That's just that equation for a tangent line, y equals f at a plus f prime at a times the quantity x minus a, the stuff I wrote up earlier. Right, that's this here from the last problem. So look, we're given, so this is just, again, linear approximation. Finding a linear approximation is simply finding the expression for the tangent line at a particular point. So nothing you're unfamiliar with from previous chapters, previous videos. So the function we're given, right, f of x is this cubic polynomial, right? -1 times x cubed plus 3 times x squared plus 4x plus 4. And then the value of a they mentioned to us here is, -4. So again, the linear approximation, this tangent line function that they're calling L of x, and it's just the value of the function at the input of a plus the slope of the tangent line, right? So f prime at a times, and then you're changing x, right? X minus a. So here, that would be the value of f at -4 plus, the value of f prime at -4 times, and then x minus the quantity x minus -4, which becomes x plus 4. So I just need these two things and pop those in. So the value of f, the actual value of the function at -4, and that's the opposite of -1 times, -4 cubed plus 3 times -4 squared plus 4 times -4 and plus 4. So this is positive 64, right? This would be -64, but then you got the opposite of it. Then plus 48, right? 3 times 16, but then minus 16, and then plus 4 at the end here. All right, so all told, that's 120, 132 minus 16 would be 116 plus 4, 120. Okay, so this is 120 in this first term, and then f prime at -4. Well, first let's go f prime at x, and just get the derivative function anywhere, and then we'll plug in -4. So again, simple polynomial here, just going term by term, applying the power rule. So that'd be -3 times x squared, plus 6 times x to the first, plus 4. And then f prime at -4. Right, so I'm just going to write out the numbers. -4 squared is 16 times -3 would be -48. And then 6 times -4 would be -24 for the next term. And then you still have this plus 4 at the end here. So that's negative 72 plus 4 be negative 68. All right, so that's going here for the slope. So I'm just going to enter this with the 120, then minus 68 times the quantity x plus 4. And if you want to distribute and put it in slope-intercept form, you can, mx plus b, you can, but they are not asking for that. So there was the value of f at negative 4 was 120, plus, and then, the value of f prime at negative 4 was negative 68, so I got minus 68 there, times the quantity x minus negative 4, which is x plus 4, and this should be good. There is a perfectly good equation for our tangent line. Y equals, or L of x equals, this expression here. Whoops. All right, so maybe, all right, let me go back and check my arithmetic. Let's see. I did make an arithmetic error. My apologies. Yeah, this 64, I think I said this was 132. This is only 112. Yeah, and then this is minus 12 here. So sorry about this, the value, and I'm sure you were screaming at the screen, the value of the function at negative 4 is 100, not 120. All right, so let's go back and change that. Nice thing about the fill in the blanks is they often give you a second chance. So I put in 100 here, so I didn't make an error on the derivative, so it should still be minus 68 times x plus 4 there. And submit. Here, that's a lot better. All right, great. See, and like I said, they put it in slope-intercept form. And maybe if you want to double check yourself, go to Desmos, make the graphs, right? The graph of the function, and then the graph of the derivative, and look at what happens near the point where x equals negative 4, and see that the L of x function actually looks like it's tangent to the curve at that point. All right, so again, my apologies for the arithmetic error. All right, so back to using a tangent line, right? Using this L of x, this linear approximation, to estimate a function value. So for us to use an appropriate linear approximation, estimate the cosine of 90.5 degrees. And then round your answer to 3 decimal places. All right. So notice how this 90.5 degrees is pretty close to 90 degrees, which would be pi over 2 radians, right? Remember when we're doing derivatives in calculus, should probably stick to radian measure. I mean, you can keep it in degree measure, but then you got to remember the conversion factors and all that. I mean, I'm still going to be doing conversions here anyway, but so we're asked to approximate or estimate, the cosine of 90.5 degrees. So again, what I'm going to do here is convert, and this 90.5 degrees is, close, half a degree off. It's close to just 90 degrees, which we'll call pi over 2 radians, rads, radians. And then half a degree I'm going to multiply that by, remember the conversion factor was pi radians per 180 degrees, and that'll cancel your degrees. So the change in x here, how much we're increasing this by is, pi over 360 radians, right? This is going to be the change in x. So look, we're looking at the function we're looking at here, which I'll call f, is the cosine of x, right? This is the cosine of some value. And we're going to be, near x equals, 90 degrees, but, again, calculus stuff, you should really convert back to radian measure. So let's find our tangent line, right? So find the tangent line to the cosine curve at x equals pi over 2. So remember that linear approximation, this L of x, and it's going to be the value of my function at pi over 2 plus then the slope, right, the value of the derivative, f prime at pi over 2, multiplied by, and then, the change in x, the quantity x minus pi over 2. Again, this is also just going to be delta x when we're done here. That'll end up being this pi over 360, but now the value of f at pi over 2, right? Remember, cosine of pi over 2, cosine of 90 degrees, pi over 2 radians, that was 0. And then f prime. Now if f is the cosine of x, f prime is, the opposite of sine, negative sine of x. And at pi over 2, remember the sine of pi over 2 was 1. So this is negative 1, this slope. So here's our tangent line at pi over 2 to this cosine function. The tangent line is simply 0 minus 1, so the opposite of x minus pi over 2. Now if you want to distribute the negative, you could, right? That's pretty easy with this one. It'd be the opposite of x, then plus pi over 2. And then when we go to our 90.5 degrees, right? So when x equals, 90.5 degrees, which if I change that to radians, that's pi over 2 plus, again, pi over 2 is 90 degrees, plus that half degree, and half degree was this pi over 360 radians. So when I plug that in, right, the value of L, right, the value of my tangent line at this input, pi over 2 plus pi over 360, and will be equal to the following. It's just going to be the opposite of this. Against the opposite of my input, so the opposite of this pi over 2 plus 360, pi over 360. Then plus pi over 2 afterwards. That was after distributing the negative. Then I distribute this, take the opposite of this, and you get the negative pi over 2 plus the pi over 2. So we end up with negative pi over 360. Remember, since we're near pi over 2, the value of the tangent line here should be approximately the same as the value of our function at this pi over 2 plus pi over 360, or the 90.5 degrees, right? So negative pi over 360 should give me a good approximation of the cosine of 90.5 degrees. Now this is something I'm going to have, they asked me to round. All right, they said round your answer to 3 decimal places. So this negative pi over 360, go to a calculator for that, right? So look, I'll go back to Desmos here. Now, if you want to go degrees, sure. I changed to degree mode. Here's the actual value. Cosine of 90.5 degrees, right, is this negative 0.00872. This is the actual value out to so many decimal places, right? That's not the end of it. It's just an approximation. Now, when I went into the tangent line, we ended up with, negative pi over 360. And look at that's pretty close. That actually gives me the value of the cosine of 90.5 degrees, accurate to the first 5, 6 decimal places here. Now we're only supposed to be rounding our approximation to the nearest thousandth. So negative 0.0087. Since that fourth decimal place is 5 or higher, I'm going to make that negative 0.009. Right, so the cosine of 90.5 degrees is approximately negative 0.009 when rounding my approximation to 3 decimal places. Right. So again, using, it's another one where you have to set up your own function. It's the cosine of x, and then you're finding the tangent line to that curve at a nice value. So here it was at 90 degrees or pi over 2 radians. And then you're plugging in, again, the 90.5 degrees in radians, plugging that into the, formula for the tangent line to get a good approximation. All right, so this is another one where we're just asked to go and write an expression for the tangent line's output. All right, y equals, now again, you can go mx plus b, or that f at a plus f prime at a times the quantity x minus a, which I'll be doing. Let's grab the paper here, sorry. So the function we're given is, the square root of x plus 1, which I'm going to write this way for the derivative, x plus 1 to the half power, same thing. And we're asked to, find basically the equation of the tangent line function at the point on this curve where the input is 35. So again, my tangent line function, this L of x, will be, we'll take the value of the function at 35, then add to that the slope of the tangent line, f prime at 35, times, and then the quantity, x minus 35. So need these values here. Now f at 35 is no problem. All right, that would be the square root of 35 plus 1, which is the square root of 36, which is just 6, right? So putting 6 here. And then I find the derivative. Now f prime would be, if I look at it this way, it's half of x plus 1 to the negative half power, then times the derivative of x plus 1, but the derivative of x plus 1 with respect to x is just 1. And if you want to write this with roots, this would be 1 over 2 times the square root of x plus 1, right, because that's to the negative half power, so it'd be 1 over x plus 1 to the half down there with the 2. Then the value of this derivative at 35, right, so f prime at 35 would be 1 over, 2 times the square root of 36, but that's just 2 times 6, so that's 1/12. Okay, so that's what I'm putting here. And this is it. Now I'm going to enter this expression. Now again, if you want to distribute the 1/12 and put the constants together, get it in slope-intercept form, that's fine, but they are not asking for that. So L of x here is, 6. That was f at 35, the function at 35, plus the slope of the tangent line at 35 is 1/12 times the quantity x minus 35, right? And this linear function should approximate the original function, pretty closely when you plug in values that are, close to 35. Great. Again, they distribute the 1/12 and put it in, slope-intercept form, but that's not necessary. All right, so back to an estimate, again, use a tangent line to some curve to estimate some value. So this time we're asked to approximate, 1 divided by 10.01. So you see how this value here is near 10? So if I look at the function f of x equals 1 over x, near x equals 10, and near, then we'll be at this, again, this is pretty close. This is only 0.01. This is only 1/100th away from 10. So again, 1 over something, 1 over some value, near x equals 10. So what I want to find now is the tangent line, this linear approximation, L of x. So again, just like all the others, I want to, L of x, the output for the tangent line at x equals 10, be the value of the function at 10 plus the value of the derivative, f prime at 10, times the quantity, x minus 10. Now the value of this function at 10 is simply 1/10, right? 1 over 10, you can put 0.1. Now the value of the derivative, right? F prime, remember this is x to the minus 1 power, so it would be negative, x to the negative 2 power, which is negative 1 over x squared if you write it without negative powers. So f prime at 10 would be minus 100th. So the slope is negative 100th, right? You plug in 10 for x in the derivative function here, times the quantity, x minus 10. And honestly, this time, because I see it, something nice will happen here. If you distribute the negative 100th, you'll end up with the following. So my tangent line approximation, L of x, is negative 100th times x, and then you got 1/10 here, plus another 10th. So 1/10 plus, 10 over 100 is 1/10, so that's plus 2/10, which, I could write as 1/5, 0.2, whatever. So now notice back here, right, we're going to plug in 10.01. Right, so the value of this linear function, this line I got here at 10.01 should be approximately equal to the original thing, f at 10.01. Right, this 1 over 10.01. All right, so let's find this. So this is going to be well, this actually, you know what? I like it, but I know this turned out okay, but I do like this better. So I'm going to go back to the way I had it initially. So this is going to be 1/10 minus, 100th times, and then, 10.01 minus 10. So that's 1/10 minus, and then this is 100th, 10.01 minus 10, that's 0.01, that's 100th. And then, 100th times 100th is 1 10,000th, right? One with 4 zeros there. So this is 0.1 minus 0 point, and then 1, 10,000th is 0.001. So we end up with the following, 0 point, and this is, throw a few zeros on this. This would be 1,000 10,000ths minus 1 10,000, so 999 10,000ths. Like this, 0.0, and that's 10th, 100,000, so 0.0999. Now they want us to round to 3 decimal places though, so approximately 0.099, but then the next one's 9, so I'd bump all this up. So instead of 99 thousandths, I'd bump it up to 100 1,000, just 0.1, 100, just 0.1 when I round that to 3 decimal places. So this is very close to 0.1. Okay, which you probably could have told me without doing a line there, right? This is very close to 1/10, right? And the denominator is almost 10. They go through all the stuff here. Okay, so now we're asked to do more of the same. So again, we're asked to use our tangent line, right? Linear approximation to estimate the square root of 8.98, which I hope you understand that this is close to the square root of 9. All right, so we're asked to estimate the square root of 8.98. So I'll look at the function. So my original function here is just the square root of something, right? This is the square root of x. And we're going to be near, x equals 9, right? 8.98 is very close to 9. So then we'll find our tangent line. All right, let's go tangent line to this curve, the square root of x function at x equals 9. So again, L of x, the value of the function at 9, plus the value of the derivative at 9, times the quantity x minus 9. Now the square root of 9 is just 3. The derivative, we saw a similar one with a root earlier. This is 1 over 2 root x. Right? This would be half x to the negative half. So the derivative at 9 is 1 over 6, right? 2 times the square root of 9 down here. So plus 1/6 times the quantity x minus 9. So there's our linear function that should approximate this square root curve near 9. And then we're plugging in, 8.98. Right? This square root of 8.98 should be approximately the value of this tangent line at 8.98. So that'll be 3 plus, and then 1/6 times, and then when you plug in 8.98 here, 8.98 minus 9 would be negative 0.02. Okay, so we get 3 and minus, now this is 2 over 100 here, right? 2/100ths, which is 1/50th. So 50 times 6. So this is minus 1 over 300. So, and this would be 900 over 300 minus 1. So 899, divided by 300. which I'll round to 3 decimal places. All right, so let's go to a calculator here. Again, they're saying round to 3 decimal places. So this was from an earlier problem. Here's 899 divided by 300. So 2.997. All right, 66. So I would round to 2.997. Okay, so here's what I'm going to be entering. And 2.997. Now let's actually check it, compared to the actual value, see if it's any good. All right, it should be reasonably good if we're close to 9. So remember they wanted the square root of 8.98. And look, yeah, that is pretty good, right? This would be 2.996, 2.9966, right? They're very, very close to each other. So our value on the tangent line at 8.98 is very, very close to the value on the square root function, at 8.998. So yeah, I'm entering that approximation rounded to 3 decimal places, 2.997. Great. All right, so then we're back to writing, the equation of the tangent line at a given point. All right, so we are given a function here that I'm definitely going to rewrite in a better way for the finding of the derivative. So this function we're given is, the opposite of, and then the numerator has negative 2x minus 3, the denominator has 2x, and the value we want the tangent line at is at negative 1. Now I'm going to rewrite this. Okay, the opposite of the numerator there is just 2x plus 3. And then if I divide each of these by 2x, 2x over 2x is just 1. And then we have plus, 3 halves times x to the negative 1. All right, 3 over 2x. So that'll be a lot easier. So our tangent line, right, L of x, again, it's the value of the function at negative 1 plus the value of the derivative at negative 1, then times, that slope times the change in x minus negative 1, which would be x plus 1. Now when I plug negative 1 into this function, and you just go here, the numerator would be 1, the denominator would be negative 2. So that's negative 1/2 for the output, the value of f at negative 1. So, yeah. Then f prime. So again, here's the way I rewrote f. Now f prime at x, so this could be negative 3 halves times x to the negative second, which would be negative 3 over 2x squared. And when I plug in negative 1 to this, negative 1 squared is positive 1, so it's just negative 3 halves. I got minus 3 halves times the quantity x plus 1. And here we go. This is what I'm going to enter. Again, if you want to put this in slope-intercept form, you can. But there's a perfectly valid expression that would give me outputs on my tangent line to this original curve at negative 1. And hopefully, again, hopefully I did the arithmetic correctly, unlike that one problem. So again, the value of f at negative 1 was, negative 1/2. And then plus, the derivative at negative 1 was negative 3 halves times the quantity, and then, x minus negative 1 or x plus 1. That should be good. Okay. And doing the same thing here for the cosine function at, 2 pi over 3. So again, just simply how am I calculating outputs on the tangent line to the cosine curve at 2 pi over 3. So our linear approximation, tangent line, again, is going to be the value of the function at 2 pi over 3 plus the value of the derivative, f prime at 2 pi over 3 times the quantity, x minus 2 pi over 3. All right, so the cosine of 2 pi over 3. So remember the cosine of pi over 3 was a half, right, 60 degrees. Cosine of 2 pi over 3, though, being a quadrant 2 angle in standard position would be negative half. So this first value here is negative half. And then the derivative, remember f prime, the derivative of cosine of x is negative sine of x. And, sine of 2 pi over 3, that was positive root 3 over 2, but, you have the negative in front. So our derivative at 2 pi over 3 is, negative root 3 over 2. And then, that slope times the quantity x minus 2 pi over 3. Again, this is all I'm going to enter. Right? They do not ask us for slope-intercept form or anything like that. Just there's how I would calculate outputs on the tangent line to this curve, at 2 pi over 3. So again, the value of the function at 2 pi over 3, negative half. The value of, the derivative at 2 pi over 3 is negative square root of 3. I actually have to, it's not like Desmos. Do the keyboard there for square root. So square root of 3, get out of there, divided by 2. And that times the quantity x minus 2 pi over 3, and pi is also in the keyboard there. All in the parentheses there. This should be enough for the tangent line. Great. So this one's an interactive one. So we're moving some points around. So let's read through this carefully, right? It says using the graph of f below. Find the linear approximation of f at x equals 1. And use the approximation to estimate f at 1.4. So 1. Drag the movable purple point to draw the correct linear approximation of f. So look, we want at the point where x equals 1. So see right now, the purple point is at the point where x equals 3.5. So I want to move it left here to where x equals 1. Right there, 1, 1. And then the black line there is the tangent line. All right. So I move the purple point to the point where x equals 1. And drag the movable red point to display the estimate. This is the movable red point. So we're going to 1.4. Right, so right now, see, the point is at 2.8. I'm going to 1.4. So 1.9, 1.7, 1.4, right there. So you see how A equals 1.4. See, drag the movable red point to display the estimate of f at 1.4. And that estimate, so you see the actual value of f at 1.4 is 1.1186, where the value of the tangent line at 1.4 is, 1.133. So they're good to the first, tenth, and that's about it. Because now the closer we got, the better. But this is what they're asking us to do, and then submit. Great. All right. So that takes care of those two. So now that I'm done with that, all right, so we're done with the linear approximations of function at a point objectives. So now we're into this part where again, I'm going to go over another discussion here first before I get into problems for differentials and calculating error and talking about relative error, percent error, and all that. All right. So this will be a talk on differentials, which I'm going to have a pretty similar picture to the picture I had earlier when discussing linear approximations. So again, suppose I'm given some function that we'll call f, and I'm going to assume that it's differentiable and continuous at some x equals a. So again, a nice generic picture of some function here. And put up a nice little swoopy one. So here's the graph of y equals. I need some new markers. So there's a graph of f. Now I go to a particular value, again called x equals a. So here's f at a, point a, f of a. And then we go a bit off of it. Now I'm going to go quite a bit off of it so we can tell the difference. So again, this distance here that I'm going off of a, and delta x. So here's a plus delta x. I plug this into the function. Gives me a point up here with the with the output f of a plus delta x. And as I showed you earlier, this change in the outputs here, I call that delta y. All right, so we've seen these already. So when you see the delta show up, so delta x, delta y, so these will represent changes on the actual curve. So changes on the actual curve, y equals f of x. So I'm going to draw this tangent line back in again. Remember how we were trying to approximate this value of f at a plus delta x. We're trying to get an estimate of that, an approximation of that, using a tangent line. So again, here's my tangent line function again at the point where x equals a. So remember, this is y equals, they were calling it L of x, which was, the value of f at a plus the value of f prime at a times x minus a, right? This was all the stuff I had written up before. Now, we're doing something similar. I start here at a, f of a. And again, I go this distance that's off of a. So differentials. This is going to be notation That's going to represent changes on this tangent line function. So these are going to represent changes on the tangent line, y equals L of x. So instead of delta x and delta y, how much x changes and y changed, on the actual curve? Well, delta, it's like the Greek letter D. So changes on the tangent line, these things they're going to refer to as differentials, will be represented by dx and dy. Okay, so again, you see dx and dy. These are going to represent changes on the tangent line. Now I'm going to make the same change in x, okay? So go from a, and we got af of a, which would be the same as a, L of a, right? Because this point is on both the curve and the tangent line. So a f of a, f of a is the same value as L of a. And then I go to this same other output. So delta x will be the same thing as dx. The change in x for the function, the actual curve, will be the same as the change in x for the tangent line. So here's where things get a little different. So I go to this a plus, dx value, a plus delta x, a plus dx. Plug that in to the tangent line function. So again, here's the value of the tangent line at a plus dx, or a plus delta x. And then the distance between those, how much the output changed there. Again, f of a is the same as L of a. So that change, so the change in the tangent line outputs, they're going to call that dy. So again, I'll make a little drawing here with it. So you see the horizontal change, dx, vertical change on the tangent line here, dy. And so you see how dy over dx, right? The change, that's rise on the tangent line over run. That's going to give me the slope. So f prime at a, right? That's rise over run. And then if we put the change in x over here, we get the following, right? That the differential of y is equal to, f prime at a, the slope of the tangent line, times the differential at x. So I'm going to keep this in a bubble. We're going to use this in other problems coming up. So the differential of a function, so the differential in y is its derivative times the differential, how much the input's changing. So the change in output on a tangent line, again, is the slope, f prime, times the change in input, dx, on the tangent line. All right, now where this comes into play with approximations. So I mentioned this before. As delta x goes to 0, right, so you get smaller and smaller. So move this point this way. So make the change in x tinier and tinier. See how the point on the tangent line would go toward, this AF of A, or L of A. And then the point on the curve would also move towards that same point. So then delta y would become closer and closer to dy. So this change in y on the tangent line would be approximately the same as the change in y on the actual curve, right? So there's a huge concept as well. So if I go a little bit off of my initial value, make delta x small. The change in y on the tangent line, right, dy, should be very close to the change in y on the actual curve, which is, again, represented by delta y. Okay, so this is differentials. Now this particular objective I'm first looking at here discusses percentage error or relative error. So I'll do that up top here. So you might recall I'll talk about, I'll do relative error. So relative error, this is just a percent increase or a percent decrease. It's how much did a value increase or decrease when I change the inputs. So the relative error when you're in a change in some quantity, up top you have the absolute value. No, I shouldn't put absolute value. Usually error is going to be made positive. So maybe not, again, you can put absolute value here, but you might be able to, they might talk about positive change if it's increasing, negative change if it's decreasing. But the relative error in some quantity, it's, your new value minus your original value, and then divided by the original value. Right, so you have some original value, which, is some y value. So, and then you change it. Right, I have some original y coordinate, this f at a. I change the input, get a new y coordinate. Now the new y coordinate is simply going to be the old one plus delta y. So you have y plus delta y for the new value. And then up top here is basically just how much the value changes, right? You have the new value minus the original. Well, if you take y plus delta y and subtract y, that's just delta y. And then you calculate what portion of that, or what portion of the original value was this change. I know I've done something like this when you talk about a percentage increase, percentage decrease. But this expression right here is referred to as the relative error of y. I have some initial y coordinate, and I talk about how much it changed relative to that initial amount, right? What portion of that initial amount was it changed by? But as we stated here, this delta y, how much the y coordinate actually changes, can be approximated by how much it changes on the tangent line. So you say that our relative error in some quantity is approximately, dy over y. So I'm going to be doing this a lot when it comes to relative error. And then when they ask for a percentage error, you just change this to a percentage, right? So remember how to take a fraction, change it into a percentage. It's kind of multiply by 100, right? If this fraction ends up being like 0.5, that's 50%. Multiply by 100. Right, so this will come up here in our first couple questions, or at least this first question. Because right now I'm on the objective, calculate the relative error and percentage error using differentials as an approximation, right? Using dy as an approximation of delta y. So again, first question related to this. So you see the radius of a sphere was measured and found to be 9 centimeters, 9.0 centimeters. So you're with a possible error in measurement of at most 0.04 centimeters. So we're asked to estimate the relative error in using this value of the radius to compute the volume of the sphere. And we're asked to round our answer to 4 decimal places. So to do this, I would like to know, they're asking about volume of a sphere here. So you might have to know some formulas, right? So volume of a sphere I'll use V for volume. So the volume of a sphere is 4/3 times pi, and then times the radius of the sphere cubed, right? Because this needs to be in cubic units for volume. So if that's the volume in terms of the radius, and the differential, because again, we're going to use differentials, the D things, the D, dV and dr as opposed to delta V and delta R. So the differential of V would be dV. And again, I mentioned that the differential of a function, say y, is, f prime of x. I had a earlier, but f prime of x times dx. So the differential of your output, my volume here, is just the derivative with respect to the input. Now the input here is r, so instead of x, it'll be, r, and instead of y, I got volume. So the derivative, or sorry, the differential of the volume, dV, how much, if I drew a tangent line to this curve, right, where if again my input variable was r and my output was v, and I drew some curve, cubic curve, looks something like this. Right, this would be some cubic curve where v was, some number times r cubed. What we're given here, what we're trying to write here is the differential of v. This is how much volume will change on tangent lines to this curve, right? How much volume will change when I change the radius by so much. So I take the derivative of this with respect to r. Again, that's f prime of r here. So the power rule. So this would be 4 times pi times r squared, and then times, the differential of the input times dr. This is referred to again as the differential of v, with respect to r here. All right, so relative error. So what we're taking here, the relative error in volume, right, in V. And normally we would calculate the actual change in V, right, the delta V, how much did the volume change? They said that the radius was measured as 9.0 centimeters with a possible error. So the error in R of no more than 0.04 centimeters. So again, that's like having input 9 on the r-axis here and then going off of it by 0.04, so to 9.04, or the other way, I could say you could have measured too low or too high of 8.96. So again, this means that, the actual radius might be somewhere in between 8.96 centimeters and 9.04 centimeters. Anyway, so the change in volume, this would be, you take the volume at 9.04, the volume when the radius is 9.04, and then, take away the volume at 9, and then divide it by the actual volume at 9 centimeters, right? If I start off at 9 centimeters and had this, increase or decrease, this error of 0.04 centimeters, this is our relative error. How much would the volume have changed? And then divided by, the actual volume at 9 centimeters. What portion of the volume of the sphere at 9 centimeters would that change represent? But we're going to approximate this by, instead of actually calculating, actual volumes, and finding the actual change in volume between 9 centimeter radius and 9.04 or 8.96 centimeter radius, I'm going to approximate delta V with dV, and then, divided by V, and this will be at, at R equals 9, right? Again, this dV is what the change in the tangent line would be, and we'd be taking our tangent line at R equals 9 here. So, again, dV, R equals 9, popping that in here. Again, dr, this is your error in radius, which is the 0.04. Right? dr is a change in r, how much I would change r, for this tangent line. So dV is 4 pi, times 9 squared times, and again, this dr is 0.04. And then the actual volume at 9, right? The volume was given this way as 4/3 times pi, times 9 cubed. Now, a lot of stuff simplifies here. 4's would cancel, pi's would cancel. 2 of the 9's, 9 squared, this will become just 9 down here. And then 9/3 just becomes 3. So I end up with 0.04 up top, divided by 3 down here. And there's our relative error. Now, this would be what? 2/5. Oh, sorry, this is 4 over 100, which is 2/50ths, or 1/25th. All right, 4 over 100, 1/25th. But then divided by 3, turns that into 1/75th. And they say round your answer to 4 decimal places, right? So let me go punch 1/75th in some calculator. So here's Desmos, 1/75th, rounded to 4 decimal places, 0.01333, so 33. So 0.0133. So again, this is relative error. Now, if they asked for percent error, you just multiply that by 100. Move the decimal place to the right twice, would be about 1.33% error. So what all this is saying, it's a lot of jargon here. What this means is that if I had a sphere whose initially had a radius of 9 centimeters, if I increased or decreased the radius by 0.04 centimeters, right, was off by just 0.04 centimeters, I could expect the volume to change by 1.33% of the initial volume. Right, so if I were to increase the radius by 0.04 centimeters or decrease the radius by 0.04 centimeters, this is saying I would expect the volume of the sphere to increase or decrease by about 1.33%. All right, now we're not asked to put a percentage in though, we're asked for the relative error, not the percent error. So I go back to this initial value here of 0.0133, put that in, 0.0133. Okay. So again, your relative error is again the change in output divided by the initial output, which you're going to be approximating with, dy over y, and I know they do that with volume here, dv over v. So this is just compute a differential. All right, so this will be just x's and y's, so dy dx. So once again, given y equals some function of x, input x, output y, dy, and dy tells me about how much, the output will change on the tangent line somewhere, and that'll be equal to the slope, f prime at that point, at some point x, times the change in the input, right? So dy, this is a differential of a function at a particular value of x. Change in y equals slope times change in x. So we're given here y equals -2 times the cosine of x. We're told that x is -2, dx is -0.4, and they're asking us to calculate dy. So again, dy is just, here's our function f of x here, this -2 cosine x. Again, the differential of y, how much y would change would be f prime at x times dx, the slope of the tangent line times the change in x. And we're given a bunch of this information here. So they're specifically asking us for, the, the tangent line is going to be at x equals -2. And then we change x by -0.4, so decrease x by 0.4, and we're asked to calculate how much would the y-coordinate change on that tangent line. So I need f prime at -2. All right, this will be my slope times, and then the change in x they gave us was -0.4, and we'll multiply these. Now f prime, all right, y prime, f prime here would be +2 sine of x. So at -2, this would be +2 times the sine of -2, and then times, -0.4. So there's, and they say put an exact value, so there's dy. Now if you want to multiply the 2 and the -0.4, that'd be -0.8 times the sine of -2. And if you use the fact that sine was odd, an odd function, you could say this is, positive 0.8 times the sine of +2. Either way, this represents how much the y-coordinate would change on the tangent line to this graph here at x equals 2, -2. So that's all we're entering. dy is, again, I'm going to use the positive version, positive 0.8 times, see they say enter an exact value, exact answer. So I'm just, entering 0.8 times the sine of 2, Vn. So another one, computing a differential. So just like the last question, we're given a function of x, y is a function of x. We're told the value we're, considering the tangent line at. So I'd be looking at the tangent line to this graph at x equals 3. Remember, dx tells me how much I change the x on the tangent line. So I increase x by 0.6. And we're asked to calculate how much the y would change on that tangent line, right, using the slope, using the derivative. So again, y equals the square root of 5x plus 9. And we're at x equals 3. And again, dx is positive 0.6. So once again, how much the y would change on the tangent line will be, the derivative. So again, I'll just put y prime times, and then the change in x. So we just need y prime at 3 here. All right, so y prime, it would be half of this to the negative half, but then times 5 with the chain rule, right? So you have 5 in the numerator over 2 times the square root of 5x plus 9. And then I plug in 3, right? Y prime at 3 gives us the first factor here. Now 5 times 3 is 15. 15 plus 9 is 24. So we get 5 over, 2 times the square root of 24 for y prime at 3. And then the change in x is 0.6. And I think they ask us, to enter an exact answer. 2 goes into 0.6, 0.3 times 5 times 0.3 would be 1.5. So I'll just do this, put 1.5 in the numerator and the square root of 24 in the denominator. I'm just going to enter that as my dy, how much y would change. So dy equals 1.5 in the numerator divided by, and then the square root of 24 down here in the denominator. Now they simplified it, of course, and rationalized, made it square root of 6 over 8. But as you've seen in a lot of these problems in previous assignments, if you enter an answer that's equivalent to what they have, they should be taking it. All right, so this is just simply find the differential of a function, right? So they have the dy equals, and then fill in the blank times dx. So you already saw the blank here, right? You have change in y on the tangent line equals, and then the slope of the tangent line times the change in x. So what's filling in the blank here is just your derivative, right? F prime of x or y prime of x. So this one here, what's filling in the blank is the derivative of this function with respect to x, y prime, and I'm just going to go through the quotient rule, and I'm just going to type it out as is without writing anything, because you should know the quotient rule by now. So up top, big set of parentheses. So up top, you got, the denominator, 2 minus 4x, times the derivative of the numerator would be 15x squared, and then minus, and then the numerator in a set of parentheses, 5x cubed plus 3, times the denominator's derivative, which would be negative 4. That's all that up top, and then the denominator squared, so the quantity 2 minus 4x squared in the bottom. Now you could simplify this if you wish, but this is our derivative function, and this is how you would calculate a differential. The change in, again, the change in y, dy on the tangent lines would be equal to the slope of the tangent line, which is your derivative function, times the dx times the change in x on the tangent line. So it's really just finding a derivative. So same thing here. I'm not really going to write this out. It's something you should be able to figure out pretty easily with the chain rule. So again, you got your dy equals, and then I'm just filling in the blank with the derivative function times dx. So it's the derivative of negative 2 cosine 3x. Remember, the derivative of the cosine of something is negative sine of that thing. So I'd have positive 2 sine of 3x, but then times 3, right, the derivative of the thing inside the chain rule. So I'd have positive 6 times the sine of 3x for my derivative function there. And that's all I'm filling in. All right, so back to this relative error stuff. All right, so this one I will write out, but yeah, suppose, the side length of a cube is measured to be 5 centimeters. So let's suppose that's our initial length of the cube. And then it could possibly change. We might have made a mistake. It could change, increase or decrease by 0.06 centimeters, these side lengths. So we're asked to use differentials to estimate the error in the computed volume of the cube. And round your answer to 2 decimal places. So just the error in the volume. This isn't even relative error. They're not even asking us to calculate relative error. So the error compared to its original value, right? That ratio of, the change in y over y. They're just asking to estimate the error in the volume, which would be delta y, or delta v, right? Error in the volume. Okay, so here, this time it's about cube. All right, so here's a little picture of a cube here. Right, you got a cube. Now a cube is made up of square faces, so that means all the lengths are the same, all the side lengths, so x by x by x. So in the volume of a cube is just, again, x times x times x cubed. So then the change in volume, right, the differential of volume. So again, the actual change in volume would be approximately the same as the dV, right? The change in, so this, remember, this is actual change versus the linear change, right? The approximate linear change, the tangential change. And we calculated some differentials in previous problems here. If v is x cubed, then dv would be 3x squared, right? Your derivative function times dx. So initially x is 5 centimeters, they said. Right, they said the initial, suppose the side length of a cube is measured to be 5 centimeters with an accuracy of 0.06. So that would be dx, 0.06 centimeters, right? This is the change, how much the side length could possibly be changed by, how much you might be off. And then we're plugging these in here and getting a possible error, right? They said use differentials to estimate the error in the computed volume of the cube. And so here's how much the volume might have changed, the actual change, the actual error, delta V. We're approximating it with our differential, dV. So delta V, right, again, should be approximately the same as dV, which is, 3 times, my value of x was 5, right? So 5 squared. And then times, and then that error in x, that, possible error in accuracy by 0.06 here. And this is in centimeters, centimeters squared, centimeters, so this should be a change in volume, right? This is cubic centimeters. Yeah, so we got 3 times 0.06, well, that'd be 600, so that'd be 18 hundredths. And 18 times 25 is 450. So 450 hundredths, right? Because again, that's 6 hundredths. 6 times 75, 423. Yeah, so 450 hundredths or 4.5 cubic centimeters. So this is our possible error in the calculation of the volume. If my measurement of 5 centimeters for the side lengths was off by 6 hundredths of a centimeter, this is saying that our error in the volume, the actual change in volume, how much we're off in the volume measurement, could be as much as 4.5 cubic centimeters, plus or minus, because you could increase this, you could increase the side length by 0.06, decrease the side length by 0.06. So that's why they got the plus or minus here. So 4.5. They say round to 2 decimal places, but that's exactly 4.5. So 4.50. All right, then another differential. So again, this is something where I'm just going to type it in. You're just filling in the blank here with the derivative function, right? The derivative with respect to the independent variable, the input variable of x here. So I've already got the dy equals, and then I'm putting my derivative function times dx. Now think about this as 10 minus 3x to the half power. So it'll be 1/2 times 10 minus 3x raised to the negative 1/2 power. But then afterwards, times the derivative of 10 minus 3x, which would be -3. All right, chain rule. So again, this is good. You can simplify it if you wish, but that should be all you need to put in there is your derivative function. So there's another one where, again, all I'm putting in the blank here is my derivative function. So I would suggest putting parentheses around it, though, because remember, the entire thing is multiplied by dx. I'm pretty sure even if you don't put parentheses, they'll take it, but if you want it to be more precise, more correct, I would put parentheses around what you replace, what I put in here for the derivative function. So dy here would be, 12x to the third plus 4x. That expression there, the derivative function, times dx. Simple as that. Okay, and back to relative error. Once again, this is just like the cube problem from a minute ago. The side length of a cube is measured to be 9 centimeters with an accuracy of 0.03. So again, that'll be x and dx. And then, we're talking about the error in the computed volume. So this is the problem from earlier. It's the same picture. Volume is x cubed. The actual change in volume should be approximately the differential change in volume here, which will be 3x squared dx, again the derivative function times the differential of the input variable. But this time, x is 9 centimeters, and dx, the amount we could possibly be off by, is 0.03. So I pop those in and change. That just changes this stuff. So the error in our volume measurements, it'll be approximately the differential in the volume, which will be 3 times, x squared, so 3 times 9 squared, times, and then the differential of x, the change in x, the amount we might be off in our side length measurement, the 0.03. So it's a lot of threes here. So this is 3 over 100, 3/100ths, and then 81. 3 times 3 is 9. 9 times 81 is 729. So this is 729 hundredths, which is 7.29 exactly. Cubic centimeters, right? These are volume measurements. So there's our error this time. So if we initially measure the side length of a cube to be 9 centimeters, if we were to change that by 0.03 in either direction, the calculation in volume, the amount the volume would change would be about 7.29 cubic centimeters in either direction. So I'm putting 7.29 here. Okay, great. So this is like the radius of a sphere problem. Now notice it's a little different than the one earlier. So the radius of a sphere was measured and found to be 7 centimeters. So that'll be my initial R with a possible error in measurement of at most 0.05. So this will be dr, right? The change in R, possible change in radius. Estimate the percent. Now this is percentage error, not relative error. So again, percentage error is no problem. You just take your relative error, that ratio of the change, to the original, and just multiply by 100. Move the decimal place to the right. two places, and I'll change it to a percentage error in using this value of the radius to compute the volume of the sphere. So once again, it is a volume of a sphere problem. So again, the volume of a sphere one more time. That's 4/3 times pi, times the radius cubed. And the initial radius measurement they said was 7 centimeters. The possible error, right? So that'll be dr, how much the radius could be off by, at most 0.05 centimeters. Now the relative error, again, relative error is how much it changed. So how much would the volume change compared to the initial volume, right? So if I started off with a radius of 7 centimeters and increased or decreased the radius by this much, this 0.05, how much would the volume change when compared to the original volume? That's relative to the original volume relative error. Again, I don't usually want to find the actual volume change, though. We can estimate this with our differential of volume. So dV over V. Now again, dV here, it's just the differential of V would be the derivative with respect to R here. So again, that's 4 pi R squared times dr. So your derivative function times dr. And then V itself, again, is 4/3 pi R cubed. And we can do a little simplification here even before plugging in numbers. The 4 pi go away, the R squareds go away, and you got just R down here. And then, instead of divided by 3, I multiply by 3. So this is 3 dr in the numerator, and then just R in the denominator. And then I pop my numbers in, and there's our relative error. So the relative error is 3 times 0.05 divided by, and then the initial value of R was 7. So let me enter this into a calculator. This is from way earlier, but I had 3 times 0.05. That was 3 dr divided by R. So we get 0. The relative error is 0.02. 14, I'm writing a bunch here, 14285, blah, blah, blah. So again, this is the first several. So again, this is relative error. Just change this to a percentage, and then they'll call that percentage error. Right? This change in volume is what percentage of the original volume. So let's move the decimal place to the right twice, multiply by 100. So the percentage error is approximately 2.142. And I say round the percentage to 2 decimal places. So instead of 2.142, just 2.14%. There's our approximate percentage error. So again, my initial radius 7. If I were to increase or decrease that by 0.05 centimeters, this is saying I would expect the volume of the sphere to either increase or decrease by 2.14% of the original. 2.14. Okay, right. And then lastly, the ones where again you're just plugging numbers in and actually finding dy. Remember, dy is how much the output would change on a tangent line. And here we're talking about the tangent line at x equals 4 to this graph, the graph of this curve here. And if I were to change x by 0.3, increase x, so go from 4 to 4.3, right, we're asked to calculate how much the y would change on the tangent line to this curve. Right, so this one has a rational function. So again, y equals, got this quartic polynomial up here, negative x to the fourth minus 3, and then 5x plus 8 down here. So again, dy, once again, is y prime times dx. So I need to find y prime. So it's quotient rule. So again, denominator times the derivative of the numerator will be negative 4x cubed. Then minus the numerator times the derivative of the denominator would just be 5. Then all that divided by the denominator squared. Now I could simplify this a tad, because I'm going to be plugging some numbers into this. So if I distribute, the negative 4x cubed to these, and then the negative 5 to these, you'd have negative 20x to the fourth, then plus 5x to the fourth, so negative 15 times x to the fourth, then minus 32x cubed, and then plus 15, negative 5 times negative 3. That's all in the numerator, and then 5x plus 8 squared in the denominator. Okay, so I'm going to put this in, we're going to plug x equals 4 into this. All right, so I'm just going to punch this in a calculator. And again, dx, they're telling us the change in x is 0.3. All right, so we need y prime at 4. All right, so I'm going to go up here into Desmos. I'm just going to enter this. So up top we have, negative 15 times x is 4, so 4 to the fourth power. Then minus 32 times x cubed. 4 cubed is 64, so let's put 64 there, and then plus 15. So all that in the numerator divided by, and then the quantity, 5 times 4 plus 8, so 28 squared. All right, so I got that. And then this is, so that's the slope. That's y prime at 4. And then this gets multiplied by dx, which is 0.3. And I think we're asked to enter an exact answer. Well, I think this can be changed into a fraction here. Look at that. Okay, so there it is. You can do the little change to fraction thing, because these are all rational numbers here. So negative 2,517 over 1,120 is going to be dy. 1,517 over 1,120. Let me just double check that I entered that correctly. Yeah, that should be good. Great. All right, you're doing more of the same here. All right, so this one will be a lot nicer. The derivative is a lot cleaner. So I got some space on my paper here. So this time y equals, 7x squared, minus 2x minus 3. Y prime is simply 14x minus 2. And we're at x equals, negative 5. And they told us to change an x on the tangent line. They're changing x by negative 0.2, decreasing x by 0.2. So y prime at negative 5, that'd be negative 72. So dy is going to be negative 72 times dx, right, negative 0.2. So that's positive, 2 times 72 is 144, so 14.4, positive 14.4 for dy. That's exact. Right. All right. So again, a lot of stuff to do there. right? Differentials, right? When you're given y as a function of x, right? The dy differential of y, the differential of the output is simply the derivative function, with respect to the input variable, multiplied by the differential of the input. Dy was f prime of x, y prime of x times dx. And then you had that relative error, percentage error, which is just how much the change, how does the change in the quantity compare to its original, right? Delta y over y, which you would then approximate with dy over y. So a lot of stuff. Well, hopefully watching me go through these here, helps you out in some way when you work on it on your own. And thank you very much for watching.